Let's now look at how segments and circles relate to each other, and specifically how the lengths of segments play out inside circles. And the first situation I want to look at is one where we have two chords intersecting in a circle. So I'm going to draw two chords intersecting in this circle, and they're just intersecting in a random location. And each chord is split into two parts, and I'm going to call those parts A and B for the first chord, and C and D for the second chord. And it turns out that the product of the parts are equal for the two different chords. And here's why that happens. I'm going to go ahead and add a couple of segments to create two triangles. And it turns out that these two triangles are similar. And here's why. First of all, this vertical pair of angles are congruent. Also, these two angles are congruent to each other because they sweep out or intercept the same arc. And then finally, these two angles are congruent to each other because they also sweep out a common arc. So, these two triangles are similar, and as a result I can set up a proportion. And for the first triangle I'm going to do the ratio A over C, and for the second triangle I'm going to do the ratio D over B. Those are corresponding parts. And when you cross multiply, you get AB equals CD. So let's see that play out with a specific example. I'm going to go ahead and draw two chords in this triangle, and the first chord I'm going to assign its lengths 6 and 4. And for the other chord I'm going to assign this a length of 8, and we're going to figure out the other length over here. And we're just going to create a product. 6 times 4 equals 8 times x. So 24 equals 8x, which means x equals 3. So that piece of that chord has a length of 3. Let's now look at some lengths along two secants. I'm going to go ahead and draw two secants in this picture. Here's one secant, and here's a second secant. And I'm going to label their parts A and B, and C and D. And in this situation, it turns out that A times A plus B equals C times C plus D. So, this exterior portion times the entire secant equals that exterior portion times the entire secant. Proving this takes a little bit more work, and I will try to show you that in class at some point. But let's look at a specific example now. I'm going to draw two secants. Here is one, and then I'm going to draw a second one over here. And I'm going to assign some lengths to them. For the first secant, the exterior is 4 and the interior is 10. And for the second secant, the exterior is 5 and the interior is x. That's the thing we're looking for. So, to solve this problem, we're going to multiply the exterior times the whole and set it equal to the exterior times the whole. And we'll get 56 equals 25 plus 5x. So 31 equals 5x, and x equals 6.2. Let's look at one final scenario, and that is how the secant and tangent segments relate to each other. And I'm going to go ahead and draw in this first circle a secant, and then coming out from the same starting point, a tangent. Now, the secant is broken into two parts. I'll call the exterior part A and the interior part B. And the tangent really has no interior, so it just has an exterior, which I'll call C. And the relationship between these three lengths is the following. A times A plus B equals C squared. So what that means is that the exterior of the secant times the entire secant equals the exterior of the tangent, which is really the whole tangent, times itself. Now that too takes a little work to prove, and we may do that in class at some point. But for now, let me show you a numerical example. I'm going to go ahead and draw a secant, and then a tangent. And let's say that the secant is broken into two parts, 4 and 5. Let's see if we can find the tangent, or the tangent length. So we'll multiply the exterior of the secant times all of the secant and set it equal to the square of the tangent. So that becomes 36 equals c squared, so c equals 6. And that's it.